also as a result of classification, because essentially we want to do classification here. You look here. See? They end up getting, well, the last layer is a classification. So the idea is that you would have some hidden layers, but then at the end, each of your words and each of the documents would get a classification. Right?
Classification in what sense?
Normal classification. Like you would have some classes, and then you would put each of them in.
A type of document.
Yeah.
Type of information in there. Okay.
So question, it seems like you are putting the TF-IDF and PMI weights, using them for the same purpose. Why can you do that?
They kind of have, they both describe how much, so TF-IDF describes how this word represents, how well the word represents this document, right?
Yes.
PMI would describe how well the words represent each other.
Yes.
So they are different measures, but they are in the same scale, because they are both counts of words with a log. Sort of similar scale, but a different measure.
But it's not exact. They don't
No, it's not
represent exactly the same thing.
I don't think you have links between documents. Do you have links between documents? No.
I don't think you can.
No, you can't, exactly.
Oh, well, you could technically integrate out over the words, right? And then you get an effective similarity matrix.
Over the words of documents.
Yeah, but
I think you would use them if you have a citation network, then you would have documents, but they don't do it here. So here they just have text.
Yeah.
So we can talk about the data sets they use, but they are all just text.
So is it only one document?
No, many documents.
So how do you represent the same words among documents? Let's say that we have the same word 1 and word 2 in another
Yeah,
document.
you would have another document here, word 2, right?
Yeah.
You would have links here with different values.
And the PMI is calculated differently here.
No, it's a TF-IDF, right? TF-IDF takes a word and a document and gives you a number.
Yeah, but the PMI between the two words is calculated within a specific document, right? You slide the window inside the document and then you
I
calculate.
think you slide over all
it's
the
corpus like
Yeah.
PMI will be
the
calculated
corpus.
from the universal set of documents.
Slide over the corpus. Then you concat them and then slide over the corpus.
You're getting very specific graphs, you're getting wheels really linked up. So you take a document, you have words connected to it, and then you have another wheel, and then it's very, very specific graphs you're generating. When you think of it,
But it's very sparse.
Sorry?
It's
no,
very
it's
sparse.
very, no, it's sparse is something else.
Yeah.
It's very, very specific. You have a wheel, so you have a document, words around it, and then, edges joining it, and then another document.
Not exactly, because the corpus represents the same kind of text. So one data set would be a medical journal
No, I know,
abstract,
but you have
right?
a document, a word connected to a document.
But the
Like-
word can be connected to two documents.
I know, then you have another wheel,
Yeah.
and then you have nodes connecting from different words. It's like
Yeah.
just very, very specific graph.
I guess. Yeah. Well, it's just a sparse graph. Well connected. If there are no separate connections.
It's like a wheel,
it
really,
is.
a wheel.
So you could, in
I guess
principle,
you could do it. Yeah.
you could in principle get an effective interaction between two documents, right? By just
Yeah.
taking the sum of the
Yeah.
product of the
And that you do that because GCNs do the convolutions. If you have multiple layers, you would have connections between two documents. Let's see how it works. Yeah. Let's look at the GCNs here. Okay. So is the word graph convolutional network very new to any of you? Okay, good. So I assume we covered this here a couple of times, so we can not be too thorough. I can just show the formulas here. There are many formulas. Okay? Well, basically it's a convolution over a graph. Normal convolution will work on a grid, but here you don't really have a grid. It's a different space. So you do convolutions on that. To get the convolution, we need two matrices, they're just symmetrics of the graph. So this would be our calligraphic G actually. Vertices and edges. So these are vertices, these are edges, and edges are values. Okay. So for the G, you would get the just symmetrics, which would be, it represents the neighbors. So if you put indexes, you would have a very sparse matrix because it's loosely connected. And you would have also the degree matrix, which would say, well, the degrees of each node. Okay? Each vertex. Now, each layer, I put maybe, you can flip, I can just find the I guess. Or can I clean it?
You can flip it.
You can flip it.
Loosen it first.
I'll just write here. So the first formula, number one, to describe how each layer is defined. It's very similar to convolution. So you would have a value activation function. A tilde, I'll explain what tilde is in a second. X and the weights, okay? W is the weights, X is the feature matrix. So each node would have a feature vector, okay? And yeah.
So how would the feature vector for a word look like? I mean, for a document it's clear, right? It's like a term, frequency, something, but for a word?
No, here they initialize
Yeah, the identity matrix. So they initialize the identity matrix. Right?
one hot, yeah.
So you would take X as an identity matrix.
So you have so you would have one index per document and one index per unique word,
Yeah.
and that's your
Okay.
columns, and then they initialize as one hot.
So one word would also
So
then be one
depending on-
one hot vector. Nice.
They're all vertices. Okay?
Yeah.
And A tilde because to enforce regularity on your graph, Carlos talked about this last time, you need the same bits. Otherwise, you end up with fully regularized matrices. So A tilde is the same A followed to once on the diagram. Okay? And then you can do multiple layers of those. So in this case, they did a very shallow network. They had only two layers. The second layer was the softmax. Okay? One hidden layer and then softmax. This, which means, basically, you would look only two neighbors apart. And they said they tried deeper networks, but there was no benefit, so they didn't use it. Okay?
And where's the embedding learned? So at what point does embedding come?
What do you mean when?
I thought they also learn embedding on top of the document.
Yes, so before the classification, so before the softmax, you would have an embedding.
Okay.
So softmax do the classification before that. I think so. Then you already I think that's how it works, right?
Or is it like the?
Well, if it's one not included, what would be the weight?
Yeah.